This is video 2 for the drivetrain unit. So for this one, we're going to start talking about mechanical advantage for a lifting system. So when we go back to how to calculate mechanical advantage, we know that's the output torque divided by the input torque. So let's take a look at this example right here. We have a standard robotic arm, has a length of 0.5 meters, has a 30 Newton mass on the end, and we have a generic 393 motor at 7.2 volts. So torque is defined as a force which is perpendicular to a lever arm. So what I would begin with is I would calculate how much torque this system needs. That would be my output torque. And I see that I have 30 newtons, which is perpendicular to my 0.5 meters. So the output torque I would need is 15 Newton meters. Now, if I want to run this system with one motor, I'm going to have to use some sort of mechanical advantage. So I know that my mechanical advantage is output torque divided by input torque, and if it's a standard 393 motor at 7.2 volts, that's 1.67 Newton meters. So I would need a mechanical advantage right around 9. So now it becomes I have to figure out which gear train I need to use. The biggest gear train, if it's a non-compound, the biggest mechanical advantage I can have is between an 84 tooth and a 12 tooth. And if I put the motor on the 12 tooth, output divided by input, 84 over 12, that's 7. So a non-compound gear train is not going to cut it. You'd have to use a compound gear train. And I leave that as an exercise to you to figure out which way, which one you'd have to use. Here's another interesting example. This is a scissor lift, and we can do a little bit of math to calculate how much force or how much torque is needed. So in this particular one, we can see that the designers have used a compound gear system here to help lift up this scissor lift. For scissor lifts, we have a kind of a special formula to calculate the output torque needed. So we got the force times distance times cosine of theta, all of that divided by 2. So there's a lot of things here. The force here would equal the weight of the scissor plus whatever you're trying to lift. So really, F is just everything. It's just the mass or the weight of everything. D. This is the length of levels for the scissors. So what we would do is, it's like the length times the level. So to get the length, we would need to measure like the height of one of those X's there. And then cosine of the angle. So theta, the angle theta, is the angle between the scissor and the ground when compacted. So if I were to kind of make a quick little sketch of this, so here's the drivetrain and the chassis for our robot. And then, like, this is the first level of the scissor lift. This angle right here will be your theta. So let's think about some consequences here then. Let's say theta equals 0. So this thing is all the way down. When that's all the way down, cosine of 0 equals 1. So when that's all the way down, you need the maximum amount of torque to pick it up. As theta grows, cosine of 90 degrees equals 0. So let's say it's cosine of 45. That's 0.707. You go from 1 to 0. So in other words, as the scissor lift opens up, it becomes easier for the motor to operate the scissor lift. But as it gets farther and farther down, as theta becomes smaller, it becomes harder for the motor to operate it. So looking at this formula, we can calculate then, or at least get a good idea for the amount of output torque we need to operate this scissor lift. And it becomes harder for the motors to operate it as the scissor lift becomes more compact. All right, the last topic I want to discuss with you is on turning torque and how much turning torque you need to overcome scrub. So remember that scrub is the resistance to turn for zero-turn systems. And it comes about from the friction between the floor and the wheels. Scrub causes the damage that you see to road surfaces when construction crews use bulldozers and other equipments with tank tread. As a general rule, if you have all high traction wheels, so no omnidirectional wheels, a longer wheelbase that's narrow will have more turning scrub than a chassis that is wider and not as narrow. And there's some reasons for that. So let's take a look at some geometry here. So here we have a robot and it has all high traction wheels. We have our turning point. And when those wheels turn, they exert a force in that direction. So this is trying to make a counterclockwise turn. So these wheels are applying a force. So the torque for turning would equal this force. Now we need a force times a lever arm distance. So we need a lever arm distance that is perpendicular to the force. And we see that that's going to be that value, x. Now we have 4 wheels, so the total torque would equal 4 times this F times x. That would calculate for us the total amount of torque that we have available to turn this robot. Now as these turn, there's going to be some friction. So as this turns, there's going to be some friction pointing in this way and some friction pointing this way, that way. Friction opposes sliding. So think about how this wheel's trying to slide. Friction would oppose that. So, as this thing is turning, there's going to be some torque from the friction, which we call scrub. And that's going to be the friction times that value y. And since there are 4 wheels, it's going to be 4 times that friction times that y. And we can go a little bit deeper. Friction equals a coefficient times the normal force. And the normal force really just equals how much this thing weighs. If we're on a nice flat surface. So the scrub then will equal 4 times the coefficient of friction times the weight times that value y. Now notice that when x is greater than y, we should have more torque to turn the robot than we have of scrub going against it. So in that case, we would have the ability to make a turn. Now if we have y is greater than x, then we have more scrub, the resistance to turning, than we do turning torque. So in that case, the robot would not turn at all. So basically, looking at this type of geometry, where x comes from the width of the robot and y comes from the length of the robot, if you have no omnidirectional wheels available to you, you want to make sure that the x, or the width of the robot, is greater than the y, or the length of the robot. Now, of course, we can use omnidirectional wheels, and what these do is that they eliminate scrub altogether, but it also changes the turning point. The turning point will always be located with your high traction wheels. So if you have a robot that you want to keep the front a little more fixed than the back, you would keep your high traction wheels on the front. If you have a robot where you want the front of it to be a little freer than the back, then you want to put your omnidirectionals on the front. But all that comes down to design and how you want your robot to operate. Well, this will conclude our unit on drivetrain.